A11, measuring things, including lengths. 11, measuring things, including lengths. Physics begins with a commitment. Claims about nature must be checkable. An explanation only becomes physics when it connects to observations that can be measured and, in principle, replicated by someone else. Without that link, even a beautiful idea is still just an idea. Across the course, we study nature through observation, measurement, and modeling. Modeling matters because physics is not a list of facts. It compresses many observations into a small set of patterns expressed precisely, usually mathematically. When physicists say theory, they mean a mathematical model that makes definite predictions. Those predictions let nature answer yes or no. The underlying cycle repeats everywhere. Measure carefully, identify regularities, propose a model, predict new outcomes, and test. When predictions fail, the response isn't rhetorical defense. It's revision or replacement. That openness to correction is the engine of progress. For the cycle to work across people and decades, measurements must be shareable and stable. If a meter varied by person or a second drifted by clock, engineering and science would collapse. Technologies like GPS depend on globally consistent clocks and coordinate conventions so that timing differences can be translated into position. Reliability at that level requires agreed standards, SI, careful reporting, and treating units and precision as core content, not decoration. What is physics? Physics builds explanations anchored to measurable quantities. The cart moves because it wants to, cannot be tested. The cart's velocity increases because a net force acts is physics, because velocity and force can be operationally defined, measured, and connected by a model that yields predictions. A physical theory is a structured mathematical model linking measurable quantities and forecasting what should happen. Even when the math is mostly algebra, prediction is what separates physics from storytelling. Measure how objects fall near Earth, model the acceleration, predict the fall time from a height, then test by dropping. If the result disagrees, you diagnose. Measurement error, missing effects. Air resistance is the classic culprit, or flawed assumptions. The goal is not to win with a model, but to improve it. That's why measurement is not pre-physics busywork. It's the handshake between world and model. Without it, equations can be clever yet untrustworthy. Measuring things. To measure is to assign a value to a physical quantity as number unit. 2 means nothing. 2 meters is comparable and reproducible. Physical quantities include length, time, mass, temperature, charge, and more, but the unit is the agreed reference that makes the number interpretable. Reproducibility forces standards. If you and I measure the same table, our results should be comparable, which requires units that are both accessible, realizable in many labs, and invariable, stable across location, environment, and time. Historically, people used body parts or local artifacts. Modern science moved away from them because replication should not require borrowing someone else's ruler. From a small set of base quantities, we define many others. We will constantly use length, time, and mass, and derived quantities inherit their units from their definitions. Speed has units meters per second, acceleration has units meters per second squared, and even energy reduces to base units. J equals kg times m squared times s to the power of -2. This reduction isn't cosmetic, it's a consistency check. If a formula claims to compute energy, its units must simplify to kilogram meter squared second to the -2, or the formula is wrong. Every measurement is limited. Instruments have finite resolution, and procedures introduce judgment. A millimeter-marked meter stick cannot justify micrometer reporting just because a calculator prints extra digits. Repeated measurements scatter, and that spread reflects real limitations. Good reporting communicates both the value and how precisely it is known. The International System of Units. To coordinate measurement globally, science and engineering use the International System of Units, SI. For our purposes, the key base units are the meter, m, second, s, and kilogram, kg. Learning to think in them early prevents confusion later because your intuition and formulas develop within one consistent language. Psi-derived units follow definitions, not preference. Meters per second literally means meters per second, and meters per second squared means meters per second per second. Energy is especially useful for unit checking. 1 joule equals 1 kilogram meter squared second to the -2, so any expression labeled energy can be reduced to base units and audited. Modern SI goes further by defining units through fundamental constants rather than fragile artifacts. The kilogram used to be tied to a physical cylinder that could gain contaminants or lose atoms, quietly shifting the definition. Now it is defined through a fixed numerical value of the Planck constant. H equals 6.62607015 times 10 to the -34 joule seconds. This matters conceptually because it anchors units to constants believed universal. The unit structure already links these quantities. Since J times S equals open parenthesis, kg times m squared times s to the power of -2, close parenthesis, times s equals kg times m squared times s to the power of -1, dimensional analysis reveals how mass, energy, and time interlock. Standardization matters for derived units as well. Agreeing on units like the joule ensures results measured in one place, and decade can be used elsewhere without translation errors. That continuity is part of why physics is cumulative. SI also has to be practical across extreme scales, which is why scientific notation and SI prefixes are not extra. They prevent misreading and make comparison easier. 3.2 times 10 to the power of -3 meters and 3.2 millimeters encode the same value, with milli meaning 10 to the power of -3. You should be fluent in both. Scientific notation often clarifies calculations, while prefixes often clarify scale. Changing units. Even in SI, you will constantly convert units. The reliable method is chain link factor label conversion. Conversion factors are forms of 1, so they change units without changing the physical quantity. If 1 meter equals 100 centimeters, then both 100 centimeters over 1 meter and 1 meter over 100 centimeters equal 1. That logic is easiest to see in a simple example. Converting 2.50 meters to centimeters is just 2.50 meters times the fraction 100 centimeters over 1 meter equals 250 centimeters. Units cancel algebraically, and that cancellation is an error check. If the units don't reduce to what you want, the setup is wrong before you ever touch the calculator. Multi-step conversions repeat the same idea. To go from km to centi-m, you multiply by 1,000 meters over 1 kilometer, and then by 100 centimeters over 1 meter, watching units cancel in sequence. Treating units as algebraic symbols is a major accuracy upgrade because it forces meaning before arithmetic. One place this saves people from predictable mistakes is with squared or cubed units. Area uses m squared, and volume uses m cubed. If 1 meter equals 100 centimeters, then 1 square meter equals open parenthesis 100 centimeters, close parenthesis squared equals 10 to the 4th power square centimeters. So converting m squared to centi-meter squared requires 100 squared, not 100. For instance, 0.50 square meters equals 0.50 times 10 to the 4th square centimeters equals 5.0 times 10 to the 3rd square centimeters. The exponent on the unit forces the same exponent on the conversion factor. Length is the simplest place to practice disciplined measurement because it's directly observable. In SI, length is a base quantity with unit meter. Base means foundational for defining other quantities, not inherently more important. In practice, measuring length is mostly tool choice and method. A meter stick fits a tabletop, a tape measure fits a room, and calipers fit small diameters where millimeters matter. The tool is part of the measurement because it sets the resolution you can honestly claim. Good technique is operational, aligned to a reliable reference, often the 0 mark, but remember that ruler ends can be worn, so starting at 1 centimeters and subtracting is often more reliable than trusting the edge. Avoid parallax by reading with your eye directly above the mark. Report to the smallest reliable division. If marks are millimeters, you may estimate 1 extra digit by interpolation, but you cannot manufacture several extra digits. Precision must reflect the instrument and the method. That honesty becomes unavoidable in calculations. If a room has L equals 12.71 meters and W equals 3.46 meters, then A equals L, W equals open parenthesis 12.71 meters close, parenthesis times open parenthesis 3.46 meters close, parenthesis equals 43.9766 square meters on a calculator. But physics is not digit hoarding. The inputs don't justify 6 digits. Rounding has to be principled, which leads naturally to significant figures. Length also motivates estimation, because many lengths are hard to measure directly. Building height, cloud distance, paper thickness. Estimation produces usable values, often order of magnitude, by combining simple models with what you can measure. If 500 sheets form a 5 centimeter stack, then one sheet is 5 centimeters over 500 equals 0.01 centimeters equals 10 to the minus 4 meters. Even estimates should keep units consistent. Units anchor the reasoning. Significant figures and decimal places. Significant figures make precision visible in the digits. A measurement is a value plus a claim about trustworthy detail set by resolution and method. Reporting 3.46 meters claims the hundredths place is meaningful. 3.5 meters claims only the tenths place. Calculations must not become more precise than their inputs. The counting rules formalize place value common sense. Non-zero digits count while leading zeros do not, so 0.0032 meters has 2 significant figures. Trailing zeros can be ambiguous. In 1200 with no decimal point, zeros may be placeholders or measured. Scientific notation makes the precision claim explicit. 1.2 times 10 to the third has 2 significant figures, while 1.200 times 10 cubed has 4, same magnitude, different stated precision. Rounding rules in computations reflect simplified uncertainty propagation. With multiplication and division, the result is limited by the fewest significant figures among the factors, because relative precision limits the result. With addition and subtraction, the result is limited by the least precise decimal place, because absolute place value uncertainty dominates. If one term is only known to the nearest tenth, the sum cannot legitimately claim hundredths, even if the other addend has them. Return to the area example. 12.71 meters has 4 significant figures and 3.46 meters has 3. Because area is a product, the result should have 3 significant figures. So 43.9766 square meters becomes 44.0 square meters. Unit tracking and significant figures complement each other. Units preserve physical meaning, m times m equals m squared, while significant figures preserve honest precision. This is also where calculators quietly mislead. They display many digits without knowing your measurement limits, so you must decide what is meaningful. Rounding too early can create drift, so it's better to carry extra digits through intermediate steps and round at the end. And it helps to keep decimal places distinct from significant figures. 0.030 has 2 decimal places and 2 significant figures, while 30.0 has 1 decimal place and 3 significant figures. Very different precision claims. With units, conversion methods, and significant figures in place, measurement starts to feel like the grammar of physics. Units keep quantities meaningful. Factor label keeps algebra honest, and significant figures keep precision claims aligned with reality. With that grammar established, we can treat time, our next base quantity, with the same operational discipline. B12 time. The pattern from length carries over directly to time. Everyday language uses time casually, but physics has to be stricter because time becomes a number we plug into equations and use to compare experiments done in different labs. In SI, time is a base quantity and its unit is the second written S. The subtle point is that in experiments, we almost never care about what time is it, in the sense of reading a wall clock. What we actually measure is an interval between two events, such as the time between a ball leaving your hand and hitting the ground, or the time between two pulses arriving at a sensor. That focus on intervals is what keeps measurements meaningful across different choices of clock zero. Two students can time the same cart rolling down a track while starting at completely different clock readings, yet agree on the interval delta t equals 3 seconds. The absolute readings are arbitrary. The interval survives translation from one clock to another, one lab to another, and one day to another. That's why time appears in formulas so often as a difference like delta t, rather than an absolute t tied to someone's chosen starting point. Operationally defining time means choosing a repeatable physical process and counting it. Historically, time was linked to astronomical cycles like the day, but Earth's rotation is not perfectly steady. It drifts and wobbles. Modern SI time is tied to atomic physics, where nature offers extraordinary regularity. The second is defined using a particular transition frequency of the cesium-133 atom. It is the duration of a specified number of oscillations of radiation associated with that transition. Halliday, Ch2. The deep idea here matches Feynman's discussion of calibrating oscillators against one another. Feynman lectures Volmarter. If a phenomenon repeats with a stable period, you can build a clock by counting cycles, and you can compare clocks by seeing how many cycles one registers during a known number of cycles of another. A wristwatch, a quartz crystal, and an atomic clock are variations on the same operational story. Count something that repeats. In the lab, you usually don't interact with cesium atoms, but you do interact with instruments that translate events into timestamps. A handheld stopwatch relies on you to mark the start and stop events. Electronic timers and sensors define events differently. A photo gate records when a cart blocks a beam. A motion sensor timestamps pulses as they are sent and received, and data acquisition systems log a voltage crossing a threshold. These details matter because they define what start and stop mean in practice. When time is operationally defined, the meaning of the number delta t is inseparable from the instrument and procedure that produced it. Uncertainty enters here in a way that's easy to underestimate. A stopwatch might display to the nearest 0.01 seconds, while another displays only 0.1 seconds. But resolution is only one part of what limits the measurement. If you're starting and stopping by thumb, your reaction time becomes part of the measurement. Human reaction time is typically on the order of 1/10 or 2/10 of a second and varies with attention and anticipation. That means even if a display shows hundredths, the uncertainty of a single start or stop may be closer to plus or minus 0.1 seconds. Two reaction time errors, one at the start and one at the stop, combine into the uncertainty of the interval. The consequence is immediate. When the interval you're timing is short, reaction time can become a large fraction of the measurement. Electronic timing helps because it moves the reaction part into circuitry that responds more consistently than a person. A photo gate can time the interval for a cart traveling from gate A to gate B without you touching anything, and the timing uncertainty can approach the instrument's internal clock precision. But even then, the instrument's displayed resolution, like 0.001 seconds or 0.0001 seconds, is not the entire story. The photogate's event might be defined as the instant the light beam first becomes blocked, which depends on alignment, beam width, and the edge shape of the flag on the cart. If the cart wobbles, the blocking moment can shift. Operational thinking keeps you honest. You ask not only what number the device showed, but what physical event it detected and how repeatably it detects it. Once you start caring about time intervals, it becomes obvious why timing is so central to motion. Many introductory mechanics quantities are built from ratios and changes, and time shows up in the denominator often enough that its uncertainty can dominate. Average speed is v equals delta x over delta t, which turns two measured quantities into a computed one. If delta x is measured carefully while delta t is hand-timed with large uncertainty, speed inherits that weakness. The danger is easiest to feel when delta t is small. If a toy car travels delta x equals 1.00 meters in about delta t equals 0.50 seconds, with a timing uncertainty of plus or minus 0.10 seconds, the relative timing uncertainty is 0.10 divided by 0.50 equals 0.20 or 20%. Even if the distance is precise, the computed speed, about 2 meters per second, can only be trusted to around 20%. If instead you time the same car over 10.0 meters, making delta t is approximately 5.0 seconds, with the same plus or minus 0.10 seconds reaction time uncertainty, the relative timing uncertainty drops to 2%. The car didn't change, the experimental design did. The same sensitivity shows up even more strongly with acceleration, because time can appear squared. If you estimate acceleration from a change in velocity, a equals delta v over delta t, the denominator again makes timing uncertainty expensive. In many constant acceleration situations starting from rest, you use x equals 1/2 a t squared, so a equals 2x over t squared. Now, a small fractional error in TE roughly doubles as a fractional error in A. A quick differential estimate makes that precise. If A is proportional to t to the power of -2, then delta A over A is approximately 2 times delta t over t. So a 20% timing uncertainty can become roughly 40% uncertainty in acceleration. When early motion labs feel messy with hand timing over short intervals, it's often not the physics that's unreliable. It's that the measurement method is mismatched to how sensitive the equations are to t. All of this ties back to SI in a practical way. Speeds should come out in meters per second, accelerations in meters per second squared, and energies in joules. J equals kg times m squared over s squared, where time sits squared in the denominator. Unit discipline matters even when numbers look right. If you time something in minutes and forget to convert, your computed speed might resemble a reasonable value while being wrong by a factor of 60 when you combine it with other SI quantities. A runner covering 100 meters in 12 seconds moves at about 8.3 meters per second. If you instead treat the time as 0.2 minutes without converting and then mix that result into SI-based formulas later, the inconsistency eventually forces the mistake to surface. Physics equations are built to be dimensionally consistent, and SI is the shared language that makes that consistency transparent. Halliday, H2. A particularly common trap appears with digital displays. Students report as many digits as they see, as if the display were a guarantee of truth. If your phone stopwatch reads 3.47 seconds, but you started and stopped it by hand, you do not actually know the interval to the nearest hundredth of a second. The extra digits reflect the phone's internal clock, but the reliability of your interval is limited by the whole measurement process, including reaction time and how consistently you identified the start and stop events. Reporting 3.47 seconds suggests an uncertainty of roughly plus or minus 0.01 seconds, which would be extraordinary for a human-timed event. A more honest report might be 3.5 seconds or 3.47 seconds plus or minus 0.1 seconds, depending on what you can justify from the method. This isn't about being modest. It's about protecting your conclusions from fake precision. A concrete example makes that danger vivid. If you measure delta x equals 1.20 meters and your stopwatch reads delta t equals 0.63 seconds, then v equals 1.20 divided by 0.63 equals 1.90 meters per second. Reporting 1.9047619 meters per second creates an illusion. If the real uncertainty in delta t is plus or minus 0.10 seconds, then plausible times range from 0.53 seconds to 0.73 seconds, giving speeds from 2.26 meters per second down to 1.64 meters per second. The true speed might reasonably be reported around 1.9 meters per second with a spread of a few tenths. Once you see that, the long string of digits becomes not just unnecessary, but actively misleading, because it hides the dominant uncertainty rather than revealing it. This is also why experimentalists like procedures that turn small, fast events into longer intervals. To find a pendulum's period, you don't time a single swing. You time 20 swings and divide by 20. Your reaction time error still affects the start and stop, but it doesn't repeat 20 times, so the fractional error in the average period is much smaller. The same logic appears in Feynman's discussion of building time standards by counting many cycles of one oscillator against another. Counting lots of cycles makes a time measurement robust against small random errors. Feynman, Lectures Volume Pri. If you hold on to the idea that time is an operationally defined base quantity measured as intervals between well-defined events, mechanics starts to feel less like symbol pushing and more like careful bookkeeping of change. The equations for velocity and acceleration don't just describe motion. They quietly tell you what kinds of measurements need to be sharp for your conclusions to be sharp. That perspective sets up the next base quantity, mass, because the moment we begin predicting how motion responds to forces, mass becomes unavoidable. See 1-3. Mass measurement in physics relies on the idea that the world can be described with a small set of basic quantities, and that everything else can be built from them. Length and time feel intuitive because you can point to a ruler and a stopwatch. Mass earns its place as a base quantity because it shows up everywhere once you try to predict motion or compare how different materials behave. Mass is the property that tells you how much stuff there is in a way that matters dynamically. If you push on something, mass determines how strongly it resists being accelerated. When we reach Newton's second law in full form, F equals ma, it formalizes exactly that observation. The same force produces a smaller acceleration when m is larger. That is why mass is tied to inertia. Inertia isn't a mysterious extra ingredient. It's the observed stubbornness of objects against changes in motion, quantified by m. Everyday language blurs mass with another idea, and physics can't afford that blur. Weight is not the same thing as mass. In casual conversation, someone says, "I weigh 70 kilograms," but kilograms are not a force unit, and weight is a force. The cleanest way to see the distinction is to imagine the same person on the moon. Their body doesn't lose atoms, just because they stepped onto a different world, so their mass remains the same. But the gravitational pull changes, so their weight changes. Mass belongs to the object. Weight belongs to the interaction between the object and a gravitational field. Once you say weight is a force, you can write it precisely as W equals mg, where m is the object's mass and g is the local gravitational field strength, about 9.80 meters per second squared, near Earth's surface. The unit of force is the Newton, N, defined through base units as 1 Newton equals 1 kilogram meter per second squared. That definition does real conceptual work. It tells you the kilogram is not how much force something has. It is the ingredient that connects force to acceleration. Saying, "My weight is 700 N" is physically meaningful. Saying, "My weight is 70 kg" usually means, "My mass is 70 kg," with Earth's g assumed. Confusing kilograms with newtons leads to dimensional nonsense. The algebra may still run, but the physics no longer means anything. In SI, the unit of mass is the kilogram, abbreviated kg, and it should be your default unit when you model physical situations, unless you have a strong reason to use grams or atomic mass units and then convert. The subtlety here isn't the conversion, it's the mindset. Physics equations are an accounting system in which every term must be compatible. Using kilograms consistently helps keep that accounting honest because the derived units we use later, newtons, joules, pascals, are built from base units, and mass is one of the pillars. The seriousness of the kilogram is not just tradition. Any unit system is a convention, but SI's strength is that its conventions are nailed down so securely that measurements made in different labs, countries, or decades remain comparable. Historically, the kilogram was tied to a physical artifact, a particular metal cylinder stored under controlled conditions. Real objects can change through contamination, material loss, or surface changes, which makes that approach a nightmare for precision science. Modern SI avoids that vulnerability. Today, the kilogram is defined by fixing the numerical value of a fundamental constant of nature, the Planck constant h. In SI, h is exactly 6.626070015 times 10 to the minus 34 joule second. Since 1 joule equals 1 kilogram meter squared second to the minus 2, this definition locks the kilogram to a reproducible relationship among mass, length, and time through quantum physics. You don't need quantum mechanics yet to appreciate the point. The standard for mass is no longer a single object that must be protected, but a rule that can be realized anywhere with the right experiment and will match worldwide. How mass is measured depends on what the instrument actually does. A balance measures mass by comparison. In a classic two-pan balance, you place an unknown object on one side and known standard masses on the other, adjusting until equilibrium. Gravity appears on both sides and cancels out. If you took the same balance to the moon, the object and the standard masses would both have smaller weights, but in the same proportion, so the balance would still compare masses correctly. That is why balances are conceptually tied to mass rather than weight. A bathroom scale works differently, and this is where confusion often starts. Most common scales sense a force, typically the normal force you exert on the scale as it supports you. Standing still on Earth, that sensed force is essentially your weight, W equals mg. The scale then converts that force into a displayed number. For everyday users, it is calibrated so that under Earth's standard gravity, it displays a number in kg, intending that as your mass, but what it physically senses is force. The displayed number equals your mass only if the calibration assumes the right g and you are not accelerating. In an elevator accelerating upward, the scale reading increases, not because your mass changed, but because the support force changed. Later, when non-inertial frames appear, this becomes a vivid reminder. The scale measures an interaction, not an intrinsic property. A numerical example helps separate intuition from habit. A backpack of mass 10 kilograms has weight on Earth. W is approximately open parenthesis 10 kilograms, close parenthesis open parenthesis 9.80 meters per second squared, close parenthesis equals 98 newtons. On the moon, where g is approximately 1.62 meters per second squared, the same backpack weighs W is approximately open parenthesis 10 close parenthesis open parenthesis 1.62 close parenthesis equals 16.2 newtons. Its inertia does not change. If you shove it sideways across a frictionless surface, it resists acceleration the same way in both places. What changes is the force needed to hold it up against gravity. This is exactly why kilograms cannot be a force unit. Forces can change with environment, while mass is meant to be an object property. Once mass is in place, derived quantities start to feel less like new inventions and more like structured combinations. Density is one of the first examples. It is defined as ρ equals m over v. mass per unit volume. When you hold same size chunks of aluminum and notice lead feels heavier, density is the bridge from sensation to calculation. If both chunks have volume, V equals 1.0 times 10 to the power of -4 cubic meters, which is 100 cubic centimeters, then aluminum, with density about 2700 kilograms per cubic meter, has mass M equals RHOV is approximately open parenthesis 2700 close parenthesis open parenthesis 1.0 times 10 to the -4 close parenthesis equals 0.27 kilograms. Lead, with density around 11,300 kilograms per meter cubed, has M is approximately 1.13 kilograms for the same volume. The units are doing quiet work here. Kilograms fit naturally because density is fundamentally about mass, not weight, and that keeps the concept connected to inertia and motion, rather than tying it incorrectly to gravity. Mass also threads directly into energy, and this is where unit grammar becomes especially valuable. The joule, J, is the SI unit of energy, defined as 1 joule equals 1 kilogram meter squared second to the -2. That matches the structure of kinetic energy, K equals 1/2 mv squared. If m is in kilograms and v is in meters per second, then mv squared has units kilogram times open parenthesis meter per second, close parenthesis squared equals kilogram times meter squared times second to the power of -2, which is exactly a joule. The kilogram isn't just a label you attach to a measurement. It's part of the machinery that makes different parts of physics fit together. Halliday H2. There's a familiar misunderstanding that shows up around here. Students learn weight is mg, then see gravitational potential energy written as mgh, and start to feel as if mass only matters when gravity is present. Gravity is simply a convenient way to turn mass into a force in everyday life, which is why people conflate the two. But mass is broader than gravity. Even in deep space far from planets, mass governs how an object responds to pushes, collisions, and forces from engines. Later, momentum P equals mv will bring the same point back with even more force. Mass controls how hard it is to change an object's motion, regardless of whether gravity is involved. Keeping the distinction clear prevents many later confusions. When a problem gives you a 2.0 kilograms cart, read that as this cart has a certain inertia, not this cart has a certain downward force. If you need the downward force, compute it as W equals mg with the appropriate g, and keep the units honest by writing newtons. When a device gives you a number in kilograms, ask what it actually sensed. Did it compare masses like a balance, or did it sense force like a spring scale and then convert? That habit, interrogating what a measurement really means, turns physics from formula memorization into reasoning from clear definitions. Closing concepts. Closing concepts. Measurement can feel like housekeeping until you notice what it makes possible. The moment two people in different places can measure the same phenomenon and agree on what they found, physics stops being a private experience and becomes shared knowledge. That shared structure connects a classroom experiment to a materials test in an aerospace facility and a timing measurement on a smartphone to the navigation solution your car computes. Reproducibility isn't just philosophical, it's a practical requirement. GPS makes the point sharply. Satellites broadcast timestamps, receivers compare them, and position is inferred from differences in signal travel time. If a second or a meter drifted depending on who measured it, the system would unravel into inconsistent answers. The same logic applies on smaller scales. If you measure the acceleration due to gravity in your classroom and someone else measures it in another city, comparison only makes sense if your standards and units are aligned. That is why physics begins with quantities you can, at least in principle, measure. Length, time, and mass are not concepts floating in the air. They are names for operations performed with instruments recorded in agreed-upon units. SI gives that agreement a globally consistent backbone, anchored by base units like the meter, second, and kilogram. Halliday, Shimsh 2. From those, everything else gets built. Energy may sound like a new kind of thing, but its SI unit has a clear ancestry. 1 joule equals 1 Newton meter, and 1 Newton equals 1 kilogram meter per second squared. So J equals kg times m squared per s squared. Chasing units back to base units isn't trivia. It's a powerful way to check whether an equation is even allowed to be true. If one side has units of kilogram meter squared per second squared, and the other comes out as kilogram meter per second, something has gone wrong before you ever compute a number. The same structural thinking is why conversion is not about memorizing ratios, but about multiplying by a carefully chosen form of 1 so units cancel. A track that is 120 centimeters long becomes meters by writing 120 centimeters times 1 meter over 100 centimeters, letting centimeters cancel to leave 1.20 meters. The cancellation is the point. It makes the arithmetic almost secondary. Even conversions that look intimidating, like turning 55 miles per hour into meters per second, reduce to arranging factors such as 1,609 meters over 1 mile, and 1 hour over 3,600 seconds, so miles and hours disappear. Units behave like algebraic objects, and factor label conversion is dimensional algebra done carefully. Precision is where many students feel the sharpest difference between math class habits and physics reality. A measurement is not an abstract real number. It is a statement about the world filtered through an instrument with limited resolution and through a human making judgment calls. If a meter stick has millimeter marks and you report 2.000000 meters, you aren't being impressively exact. You're claiming knowledge you don't have. Significant figures are the grammar that keeps claims honest. If you measure a tabletop as 1.26 meters, those digits tell the reader what level of detail is trustworthy. Then, if you compute an area, A equals open parenthesis 1.26 meters close parenthesis times open parenthesis 0.84 meters close parenthesis equals 1.0584 square meters. The physics-friendly answer is 1.1 square meters, because multiplication shouldn't create fake precision. It should reflect the least precise input. The same mindset is why you'll see 9.8 meters per second squared rather than 9.800000 meters per second squared, unless the measurement method truly justifies those extra digits. Taken together, the thread is that physics is a language designed to travel well. SI units make statements interpretable anywhere. Derived units keep complex quantities traceable to shared foundations. Factor label conversion makes unit changes mechanically reliable, and significant figures prevent you from overstating what you know. With that in place, equations can function as bridges between measurement and prediction rather than as symbols on paper. That foundation is exactly what we need for what comes next. Once you trust your units and your precision, dimensional reasoning becomes a tool not only for converting numbers, but for building and checking equations before you plug in data. When we begin describing motion, an expression like x equals x naught plus vt won't be believable because it looks right, but because every term carries the same units of length and the measurement assumptions are realistic. If you keep treating units and significant figures as part of meaning rather than decoration, physics becomes less about guessing the right formula and more about making statements the world can't easily contradict.